Hi and welcome back to this latest video. We've got the whiteboard out, means there's going to be some talking. As you can see from the title, we've got low ohmic resistance tester, a piece of test equipment that we want to design and build, and I wanted to explain what the purpose of this low ohmic resistance tester, as I've decided to call it, what the point of this tester is. Now of course you can use a multimeter for measuring very low resistances. We're talking anything down to 1 ohm or possibly less than 1 ohm, half an ohm, 100 milliohms, that sort of range. That's the sort of resistances that we're looking at wanting to test. Now why do we want to do this, and why don't we just use a standard multimeter that you can buy, which will usually take you down to about 1 or a half an ohm or something. And there's a reason why sometimes test meters fail. Test meters are not suitable for the sort of testing that we're going to talk about here. I was watching a video on YouTube the other day, and I was watching Adrian's Digital Basement. If you don't know Adrian's channel, definitely worth a check out. It's all retro computer repairs, really interesting stuff, and diagnostics and everything. So if you haven't checked out Adrian's channel, go and have a look at that. And I was watching one of his videos the other day, and he had a problem with PCB traces. He was trying to buzz them out, you know, trying to use a standard meter to see if a track was actually, you know, conducting through from one pad to another pad. And what he was finding was they were kind of like connected. If you tested it with a normal resistance meter, just on an ohm scale, you know, you might get a beep, but actually it wasn't good enough. He did it another way by actually putting current through the trace, and that enabled him to actually see that the trace wasn't really connected properly. It's really interesting stuff, and it's very rare you'll come across a situation like that in fault finding, but it does happen. So what I wanted to do here was build a resistance meter that will measure situations like that. For instance, if you're buzzing out tracks on a PCB, maybe it's on a computer board or whatever it happens to be, maybe you've got an intermittent or a trace which is kind of damaged by oxide, you know, caused by water damage or something like that. You may actually have a trace which buzzes correctly with a meter, but as soon as you start to put any current through it, it fails. That's what this video is going to be about. So let's have a quick talk about problems that you can face when trying to buzz out a track, a trace if you like. So let's just have a look at what might happen here. Let's say you've got a pad here. Okay, there's our pad, PCB green, and you've got a trace which comes along here normally, and you might have another, let's just for argument's sake say there's another pad there. Okay, so you've got a pad there from a component, and then you've got like another pad over here on the PCB, and normally you can take your meter and you can just buzz out the pads and that checks the trace, no problem at all. But what can happen is sometimes, and it usually happens at the pad itself, either this pad there or that pad there, but it can also happen in the middle of the trace if you have water damage, oxide build-up. You can get problems with the continuity, which a normal test meter may not show. It becomes a marginal situation and you might not spot it. What can happen is you can have a break in the track, and this part is, let's say that's like damaged just there, that red section there. So when you come to measure it, you may have something like 2 ohms, 3 ohms through the trace, something like that, where it should be 0.05 of an ohm or 0.1 of an ohm. What happens is, if you try to put current through that trace, 10 milliamps would be common, 15 milliamps, 20 milliamps is probably your maximum. That sort of logic level, like you could be driving from, say, a TTL chips or something like that, you might have anywhere between 5 and 20 milliamps, let's say. And if this trace is damaged by oxide, or maybe somebody slipped with a tool, hasn't quite cut the track but it's damaged the track, that's what we're talking about, then, you know, it may not be able to handle that current. It may not be able to handle, you know, milliamps worth of current. It may handle microamps because of its resistance. This basically becomes, if you like, a resistor at that point. It could also be damaged here. Maybe there's a broken track just there as the trace goes to the pad. or maybe it's broken just here. They're quite common as well. There's quite a few things that could go wrong with that trace, especially on old boards, like an old equipment where, you know, it's been subjected to moisture, as I said. You can get problems like this where a normal test meter will not actually show that there's a fault. You may get a beep, it may say beep, you know, continuity test, and everything works, but when you actually try to do it as a logic circuit, it does not work. So the trick is to pass some decent amount of current, or try to pass some decent amount of current through the trace and see what the current is, like measure the current. The important thing is that you're not just passing, you know, like 1 milliamp or you know, or 500 microamps like you know you might get from a standard cheap test meter. You know, you need to actually get current flowing, or try to anyway, and that tells you how good the trace is. What we're going to try and do is build a piece of test equipment to check for this situation. Straight off the bat, we need something where we can pass through a known amount of current. I'm sort of thinking maybe 10 milliamps would be handy. If we put 10 milliamps through the trace, you know, it could go up to 20 milliamps. Maybe, you know, anywhere between 5 and 20 milliamps is probably reasonable. I'm probably going to aim for 10. That seems to be somewhere in the standard logic level for a computer board, let's say. So, but you know, that could be changed. Rather than trying to measure the current, you know, the actual current flowing through the trace, which you can do, you can put a current meter in line, but the problem with that is you're constantly looking at the display on the meter itself. You're not getting any quick feedback like a beeper or anything like that, an audio sound. So you're constantly looking at the meter in order to check whether you're getting your 10 milliamps. So it's not very fast, but yes, you can do it that way, a cheap way. Just use a constant current source of say 10 milliamps and use a current meter. It's fine, but it's slow. I think we can do a bit better than that. So what I was thinking was, let's introduce a constant current source and put that across the trace. Like I say, let's just aim for 10 milliamps for now, although, you know, this is a matter of debate. We can then measure the voltage across the whole point to point, if you like. So we can go from that pad to that pad with a couple of probes, and at this point here we can measure the voltage across those 2 points. So that's what I'm thinking. We need 2, if you like, blocks in our device. So we need a constant current source to get the current flowing through the potentially damaged trace and measure the voltage across that. So if you think about it, it's just Ohm's law. So we can say V equals I times R. Okay, so we can say V equals the current, which is 10 milliamps in our case, times the resistance, which if it was say 1 ohm, then you would get 10 milliamps times 1, it's just 10 millivolts. So if this was a 1 ohm trace, so it's damaged, or maybe it's a very long trace through a very complicated path, you know, it could be damaged. It means that we would measure 10 millivolts across that trace. Now, obviously if the trace was in better condition or just shorter, then, you know, normally typically you'd get something like about 0.1 of an ohm. Would be probably acceptable for a trace, as long as it's not too long. That's roughly what we're looking at. Alright, so now that we know basically what we're aiming for, let's have a look at some of the blocks that we can use to achieve this. You may think this is a little bit over-engineered for what we're trying to do. There are simpler ways to do this, just using a standard comparator to check for a particular point. So here we are. Let's look at some of the blocks that we can use to implement such a device. Here's our test probes here. We're going to put our probes into these terminal blocks here, and these are what we're going to use to measure the traces on the PCB, just like you would use with any standard multimeter with a couple of probes, you know, a couple of standard probes, yeah. So they plug into here. So what we're actually going to do from the 5-volt rail, we're only going to use 5 volts. We don't want to be using any high voltages or anything. Not when you come to testing circuit boards. You really don't want to be putting 12 volts or 20 volts or anything like that. So we're going to stick with standard 5-volt logic levels. And it should also be safe enough for 3.3 volt systems as well, because it's current limited. So let's run it from a 5-volt rail, and there's another reason for that in a moment. This is going to be a 10 milliamp constant current source. Basically limit the current we can take from the 5-volt supply to 10 milliamps. The 10 milliamps, as I said earlier, it's just a figure which kind of feels right. It may be that we need to up that to 15 milliamps or 20 milliamps, but for now, I'm just going to design the thing for 10 milliamps. And this is a constant current source. If you short out, and this is our 0 rail at the bottom here, if you short out these probes, you put a wire link across here, so it's a dead short, you will only get 10 milliamps flowing through this circuit here, okay? That's the point of this. That's going to ensure that we're putting up to 10 milliamps through the trace that we're going to test with our probes. Good. Now, how do we come to actually measure it? Well, of course, you could just put a test meter across there and you could measure it. Nothing wrong with that. But like I said earlier on, it's not going to give you any audible indication. You know, it's not going to bleep. You might want to rapidly scan a lot of pins on a chip. You may just want to get your probe and go zip all the way along and all the way back. And, you know, you're not going to hear anything. You're not going to be able to see a meter react fast enough. If you're going at that kind of speed, you may want to rapidly get through a lot of pins for fault finding situations. So we're trying to do this in a way where we get some sort of audible bleep if the trace is either connected or not connected. It sort of rules out using a standard multimeter, but yeah, if you're not too bothered about it being fast, you could just put a meter across that and you could measure the voltage. So let's go a bit further. Let's measure the voltage across the tested trace, as we said earlier on, just using Ohm's law. And that will allow us to calculate the resistance of the trace. If we know the current flowing through it, okay, and we know the voltage that we're going to measure across the terminals, we can work out the resistance. R equals V over I. So let's take the voltage appearing across these two terminals and feed them to an analog to digital converter in ADC. And there are various ways we could do this, but there is a very cheap solution available from Adafruit, which is a purpose-built module which allows you to have differential inputs, which is very good. So it's not just measuring to ground, it's actually two terminals on the input of the device, and that measures down to fractions of a millivolt. And because it's got differential inputs, it takes away any problems with grounding or anything like that. So we're going to take the positive and the negative terminals straight from the actual probes that plug into the device. This particular ADC, the one I'm talking about, the purpose-built module, is controlled through I2C, I2C, and we've covered that in other videos. But basically it's a serial communications protocol. So here's our two connections here, and that connects to a computer or an MCU, microcontroller unit. And in our case, as we like in nearly all of my videos, we tend to end up using the Arduino development board for that, just because it's fast and it's cheap. So at this point, we're able to actually measure the voltage across the probes and do a little calculation in firmware to allow us to display the resistance of the trace. You might think, well, okay, here we are basically reinventing the wheel and making a voltmeter. Well, that's true, except because we'll be able to control the firmware, whereas with a meter you can't. And it means we can set a lower limit or an upper limit, if you like, depending on which way you look at it, in firmware. And if the trace is below a certain resistance, we can set off an alarm, i.e. a beeper, something audible, not just a display, which would take too long to look at all of the time when you might be looking at the probes and the traces that you're trying to test. You don't want to be looking at this at the same time unless you need to. So from the MCU, let's trigger some sort of bleeper, okay, or buzzer if you like. So as we're scanning the trace from pad to pad, the buzzer will sound below a certain preset level that we can adjust to set the alarm to tell us that we really do have continuity and it's passing 10 milliamps. That's it. That's kind of what we want to do, so we can actually make sure that the buzzer only activates when the trace is of good enough continuity or low enough resistance. And that's the advantage you don't get with a lot of test meters. You can't set the actual, if you like, the lower bound of the continuity level. They're usually preset to something like 50 ohms. So on most meters, it varies from meter to meter, but it's always built in, there's nothing you can do. Well, 50 ohms to us is useless. That's completely pointless. It would just buzz on everything. So with this, we can set it to say something like half an ohm, which would be a reasonable test point, or 0.3 of an ohm even. We'll be able to set that, and that really is going to tell us, yeah, that trace is very good. It's below half an ohm's worth of continuity. 0.1 of an ohm even, 0.2 of an ohm, them sort of levels. This is our low ohmic resistance tester. I hope that explains basically what we're going to do for the rest of the video. And now we're going to start to look at some actual circuitry to implement these blocks. So first block is going to be the constant current source, and we want something that's going to give us around about 10 milliamps. One of the easiest ways to create a constant current source, well, there's lots of ways to do it actually, but let's just say for the sake of convenience, is to use an LM317 regulator. Now this is actually normally used as a variable voltage regulator, but because it has a fixed reference inside of it, we can reconfigure it as a constant current generator or constant current source. Here's the circuit for it. It's literally two components. Plus 5 volt input to the input terminal of the regulator. We've got a resistance in the output side of it. So this is going to be our current chain from left to right, and this will go to the positive terminal of the test probe. You'll notice we've got a preset resistor in here, marked R, and we have an adjustment terminal, this third pin on the bottom here. This is connected to basically the output as well. That's kind of it. It couldn't be much simpler. So what we can do here is figure out what value of R we need to give us 10 milliamps. And of course, if we make it into a preset, we can adjust it to anything we like. And the formula for this is simply I, the current, equals 1.25 over R. And it works out, looking at my notes, that if we adjust this to 125 ohms, that will actually give us 10 milliamps, which is exactly what we want. So a suitable resistor for that would probably be, I don't know, maybe 200 ohm resistor, shall we say? A variable preset. If we say fitted a 200 ohm, that means we can adjust it all the way through, much higher than 10 milliamps, much lower than 10 milliamps. And you could always maybe make this even better by padding it out with series resistors, so the adjustment range is reduced, and that would give you a much more accurate setting for the current limiting. Just for the sake of argument, let's just stick in something like a 200 ohm preset, and we can adjust it to 125 ohms, and that's what we're going to do for this project. So let's go and have a look at the measurement side. So let's take a look at the ADC module that we're going to use. This is the ADS1115 by Adafruit. These are available all over the place, eBay, Amazon, very cheap indeed. For what they are, it's pretty incredible. These are a 16-bit ADC, and it has 4 input channels which can be multiplexed, so you can select between different input channels to take, particular measurements. There is only one ADC inside of the unit with the multiplexer connected to the input of it. So what that means is that the ADC itself is 16-bit, okay, which is way better than the standard ADC that you might find inside of an Atmel 328P microcontroller. They're usually only 10-bit at best. There are some microcontrollers out there which have better ADCs in. I'm sure if you shopped around, you could probably do away with this and actually have the input measurement going straight in to the microcontroller. However, they tend to be rather expensive, and because we need to measure down to very low voltages, like 1 millivolt, let's say, or half a millivolt, we've really got to be able to measure those very low voltages, and the ADC has to be able to handle those signal levels. And of course, what you could do is you could build an op-amp stage with gain, and you could actually increase the signal coming in before it goes into the ADC. However, another big advantage with this particular chip on this module is that it has built-in gain factors which you can adjust through firmware. You can actually set the internal gain structure of the ADC, and one of the settings is, I believe it's times 16. So whatever you measure on the input can be, it has a times 16 gain before it actually hits the ADC measurement device within the chip. And this is to a 16-bit level of resolution. Because it has that built-in gain function within the chip that you can program through firmware, it means you don't need any external circuitry. That's fantastic. I'll just take you through the pins. We've got V positive here, which is basically going to be 5 volts. We have a ground pin here to 0 volts. SCL and SDA, these two pins here, are for the I2C, the I2C bus. They will connect to the Arduino processor. There's an address pin here. Even though it's only got one pin, you can actually set 4 different addresses for the I2C bus. It depends where you connect the address pin to. If you connect it to ground, you get one address. If you connect it to positive, you get another address. If you connect it to SCL, you get a 3rd address, and if you connect it to SDA, you get a 4th address. So depending on where you connect the address pin, you have 4 different possibilities of addressable I2C locations. We're only going to be using one location, so the address pin in this particular case is just going to be left disconnected. And that'll give us, I think it's hex 48, but we'll get to that in the firmware later on in the video. So we don't really need to be concerned with the address pin here, but just so you know, you can actually address up to 4 different locations on the I2C bus. It means you could have 4 of these modules if you wanted to, all connected in parallel on the same bus. This pin here is an alert or ready pin, and this has 2 different functions. You can use it to tell the processor that the conversion of the ADC is ready. You can also do some clever stuff with limits, where you can set a high limit of the ADC reading and a low limit of the ADC reading, and you can use that as an output to alert that something, let's say the voltage is too high or the voltage is too low. Now this is interesting. We're probably not going to use this, but as an option, just know that we could actually use this for our downward limit when we come to measure across the trace. If the resistance is low enough, in other words the voltage is going to be low enough, we could actually programmatically set this up so this pin becomes active when we go below a certain level. Just so you know, that's actually a possibility. We may even get to a point where it has to become a reality. But for now, we're going to just do the whole thing in firmware for the limit checking, okay? For our set level for continuity we were talking about earlier. So let's leave that for now, but question mark, it is another way of doing it. These are A0, A1, A2 and A3. These are all analog inputs to the ADC. So these are our actual voltage inputs, which can be, it goes through a multiplexer, a MUX, which you can then select which pin you want to take a reading from. Or, in our case, 2 pins that you can take a reading from as a differential input. Okay, which leaves the other 2 pins free for something else that you might want to come up with later. But for now, we're not going to do that. We're going to be using A0 and A1, okay, as our input signals in this particular case. So these 2 pins here will be connected to the probes that the current source is connected to, and these are going to measure differentially the difference between A0 and A1, or the positive and the negative of the test probes, if you like. And that's kind of it. So this is the module that we're going to be using, and this is going to connect to the Arduino development board over the I2C bus, the SCL SDA pins here, and the whole thing runs off 5 volts. Let's go and have a look at a schematic diagram on the computer. Yeah, let's see if we can actually put something together and maybe get something to actually work. Yeah, and just a quick note, this is the actual module, the Adafruit ADS1115. These are the sort of things you can pick up super cheap. There's all the pins, silk screen and everything, tells you what they all are. And that's what we're going to use. So this is going to plug straight, we're a little header on here, it's going to plug straight into the proto board, and we can have a bit experiment with that. Anyway, that's what they look like. Okay, behold, we've put some components on one of these, whatever they're called, proto breadboardy things, which incidentally I really dislike because the contacts are always terrible on these, and it's very difficult to get a good contact when you put the connectors in. It just doesn't really connect properly. So I quite dislike them, but I'm doing this in a rush, and I'm trying to save a little bit of time with the soldering iron, the way I would normally do it, which is a much better method. So anyway, I'll just point out what we've got here. We've obviously got our Arduino development board doing Minalov. Basically that's connected to the rest of the circuit. So we have here LM317, just inside of there, if you can see that, and a little 200 ohm preset. This is our constant current source, and it really is as simple as that. It's just the a regulator and a preset resistor there, and that supplies the 10 milliamps current. So that's been supplied to where the probes would normally connect to. Then we have the ADC module that we've just been looking at earlier. There it is there in the board, and that is connected the way that we described earlier with A0 and A1 through these two wires here, the green and the brown, if you can see that. And those two wires again connect to the test probes. So basically this is supplying the current, and this is the reading the voltage across it. Then we'll have, of course, one of these displays, which is the this is a 20 by 4 matrix display, 20 by 4 character display, 2004 LCD with a backlight on it, and that is connected through the standard method of connecting to our Arduino boards, and that is using a 4 data bit system. And you can look this up on the internet. It's very common how you connect the LCD to the Arduino board itself through these cables right here. That's all the display cables. There's 4 data lines and there's 2 other control data lines, and that basically allows you to write anything you want to the screen. So that's kind of it, and what I'm hoping is inside of here, if you can see, a tiny resistor in there, and that is going to be my test 1 ohm resistor. Okay, so we're going to simulate a trace with a 1 ohm resistance, if you like, a faulty trace with 1 ohms, which would be regarded as too high normally. Now it's not a precision resistor, it's probably 1 or 2%, something like that, so the readings may not be exactly correct because of the precision of that resistor. And of course the other thing is, I've gone ahead and wrote some firmware and already done that in the Arduino IDE, and we'll have a look at that in a moment, how this all works. We'll have a look at the firmware, but let's just get something up and running here. So the firmware is done up to a point. It can be improved, but we've got it to a working situation where it's good enough to put some power on and try the thing and see what kind of measurements we're able to get. So what I'm going to do now is switch it on, apply 5 volts to the whole thing, and we'll take a measurement, should be hopefully displayed, of the resistance of the 1 ohm resistor. The other thing we're going to do is measure that the constant current source is exactly calibrated to 10 milliamps. Actually, I think I'll do that first. I think we'll get the multimeter out here, and we'll just have a look at the current flow and make sure this is set to exactly 10 milliamps. So let's do that first. Hope you can see the meter okay here, trying to get everything in shot. But we're going to be measuring current in milliamps, and the first thing I want to do is just basically short out the current source to ground and measure the current that we're actually getting. So let's do that. Okay, pretty close, 9.925. I'll adjust this a little bit, see if we can get it any better. Which way am I going? Yeah, 10.06. It's a little bit difficult to adjust, to be honest. I think I could probably do with a, there you go, 10.013. I think that's close enough. I think we can call that, for the sake of this experiment, we can call that 10 milliamps. Would you agree? Close enough. Right, so we know that the constant current source is exactly right, and that's a dead short through the meter. As I say, it will only go to 10 milliamps. You can't take any more than that. So let's connect the constant current source back to the test resistor and have a look at the LCD display and see what that's doing. All right, very good. This is encouraging. So everything's on, it's all powered up. We know we've got 10 milliamps going through our little test resistor, which is buried inside of there, the little 1 ohm resistor. And what it's telling us is it's able to measure 10 millivolts across the resistor, or what would be the trace, which is correct, 10.6 actually, according to this. And don't forget, there's some pretty bad connections going on, and when I move things around, if I just touch it slightly, you'll notice it changes a little bit. These boards are terrible for contact resistance problems, so I'm surprised it's working at all. But the main thing is now we're able to take a resistance reading, ohms here, of 1.09, 1.089 ohms. So yeah, just over 1 ohm. Very good. So that's given us, if you like, pretty accurate by the looks of it, resistance reading of what would be taken across the trace. Of course, I don't actually have any way to plug in probes at the moment. We're just experimenting right now, and I've put in that 1 ohm resistor just to get the thing up and running. So that's correct. 10 millivolts across 1 ohm does actually give you here 1 ohm. You'll notice I've got a little bit on the bottom here in the firmware. This is our set point, where you can actually set the level at which the output will be activated, and we haven't got you'll notice we haven't got any audible speaker connected or anything yet. Haven't quite got that far. I'm trying to decide whether to do it in firmware in the Arduino, just to make like a little square wave oscillator beeper thing that you connect to a small speaker so it goes buzz, or whether we need to take the output, put it through an actual something like a 555 timer or something, oscillator type circuit. There's different ways to do it. Haven't actually decided which way to go, but basically this set point will activate something. When it gets down to a certain point, it will trigger the alarm that we want to say yes, we've got good continuity below this preset resistance point. So up to now it's looking really good. It's much better if you're going to build a project like this, is to solder the thing, actually put it on a proper board, you know, whether it's Vero board or whatever, and then you get a much better physical connection. These are just completely hopeless. But I just thought, save a bit of time and, you know, throw it all together, get the thing up and running. So far so good, looking very good. Let's go over to the computer workstation and have a look at the firmware in the Arduino IDE and see how we managed to kind of put this all together. Okay, so here we are at the computer and we've opened up the Arduino IDE. And this is the firmware we have so far. Right off the bat, we are using a library, ADS 1115_WE library. This is for the ADC module. This particular library, there are different flavors of library, it doesn't have to be this one, but I quite like this one, and it's been written by Wolfgang Ewald. I hope I'm pronouncing that correctly, apologies if I'm not. And he's wrote this library, which allows us to control the ADC module. Works very well, highly recommend it. So we're including the library here, which allows us to communicate to the ADC module quite easily, in fact. We're including the 2-wire library, which is part of the Arduino standard, and it is for communicating over the I2C bus, the I2C bus. We are also including liquidcrystal.h here, which is again the internal library of the included library of the Arduino environment, and this allows us to draw characters, display characters on the LCD display. Those are the 3 main libraries that we're importing to get the job done, and we've got a little define down here, which is setting up our I2C address as hex 48, which is the default value for the ADC module if you don't have anything connected to the address pin, and in our case that's the case, so it's not connected and it just defaults to hex 48. That's the address. With all that in mind, let's continue. I'm not going to go through every single nut and bolt of this, but just to give you an outline. Here we are setting up the pins for the LCD display. We're assigning pins basically from the Arduino development board to the various pins of the display. Here we are actually telling the LCD display what mode to go in. We're not using the read-write pin, that's tied low on the display. So the display is basically in one mode only, which allows us to write to the display. We're not reading anything from the display. There's a continuity LED. This is not quite decided upon yet, but basically it's pin 2 of the Arduino development board. I've called it continuity LED for now, but this is probably going to end up being a buzzer or a bleeper output, and I haven't decided whether we're going to have an internal firmware bleeper, if you like, something which causes a square wave output on the pin. for a certain duration, like 200 or 300 milliseconds is usually long enough for a bleep, and I haven't actually done anything. So all we're doing right now is just asserting this pin, and you could connect something to that, but it's undetermined at this point. When we reach the alarm limit or the alert limit where the continuity is below the set threshold, this pin will be asserted either high or low. We've got a little bit of on display stuff going on here. This is just to put some firmware version that we are. Got some more variables here. The current that we're actually going to be using in the project, as we've said earlier, is 10 milliamps. So that's the unit under test current, if you like, constant current of 10 milliamps, which expressed as amps gives us 0.01. Minimum trip point, this is our set point, if you like, where the firmware will detect whether the resistance has dropped below a certain point. And for now, I've just got it hard set. It's not adjustable at this time. It's just hard set for 0.5 of an ohm, or 500 milliohms, if you like. And we can change this in firmware. Later, I would like to improve this so we can adjust it externally, so then we can set it to any value we like. Probably save the result in EEPROM, so the next time you come to switch the device on, it's memorized the set point you had previously. Beep time, that's the duration of the beep, and we're going to be looking at something like 300 milliseconds. That sounds about reasonable. This is a little bit of startup code where we start up the 2-wire or the I2C bus, see if there's any communication available. If there's no communication with the ADS1115 module, we shall assert a little message on the display saying failed. I've also got a little function at the end called error blink, which just turns the LED on and off a few times just to sort of show as a failure. And basically now this is all part of a splash screen, which gets displayed when you first switch on the device. It just puts some information on the screen for 1 or 2 seconds, depending on what you want to set it to. This is comments from the example that Wolfgang has supplied, and I'm leaving this in just for reference. We're actually using this scale here. You can see it's set here actually in the function parameter here, and this allows us to have an input range of plus or minus 256 millivolts. Okay, we're only using plus voltages, but it does actually read from, because it's a differential input, we can go negative as well. Basically, we're using it as 0 to 256 millivolts. And as I say, that's the setup there. This is setting the, if you like, the internal gain structure. There is an internal amplifier, and basically you can set up the gain internally, which is very neat because it means we can measure very small millivolt range, sub-millivolt even, values without any external amplification. There are comments here about the compare inputs. These basically set up the mux. This sets up what are we actually going to measure, which pins. You've got A0 to A3 on the device, and what we want is actually the default, which is this, which is compares A0 with A1, or input 0 with input 1. There it is there, set as the function parameter data. So that's exactly what we're going to do. The default is the one we actually want in our case. There are some other parameters you can set up, which we're not using. We can set up the samples per second rate here, and we've got it set to 250 samples per second, which is quite sensible for what we're trying to do. Continuous mode or single mode, this is all ADC of course. You can have it so it's not reading all of the time, it's not trying to sample all of the time, and it'll only sample when you ask it to. Or you can have it running continuously, as we are here. We've got it set for continuous, where the ADC is constantly taking in samples, and it's just up to us to dip in and poll it to see what the, read it if you like, to see what the value is at any particular time. So that's what we're doing. We're just going to let it free run and keep going, and we'll just dip in and poll it as and when we want to take a measurement. We've got a little bit of code here which is just setting the cursor to the bottom line. Why is that the bottom line? Because we've got a 3 here, and the lines are numbered starting from the top line as 0, 1, 2 and 3. That's 4 lines of course. So We want to write something to the bottom line of the display, and all we're doing is writing set, and we're entering in the set point that we did in the definition at the very beginning, and then ohms on the end of that. So all this is doing is writing out one line which says set, and then in our case 0.5, which is the minimum trip point we've set, and then ohms on the end. So that's just basically drawing one line on the screen. Then we come to the main loop. Now there's not much code after this, okay, so we're getting there. Obviously this is going round and round continuously. We've got a little delay at the bottom of 25 milliseconds, which I've just arbitrarily picked out a number out of the sky and put it in. You could probably adjust this maybe down to 10 milliseconds or up to 50 milliseconds. It really is just a case of trying it and see what the result looks like on the screen, whether the screen updates are fast enough. This function here is the important read channel function, and this is going to load whatever the ADC voltage is at this particular time and load that into our variable voltage, which is a float. And we use floats so we can use decimal points, of course. You know, we're reading millivolts and sub-millivolts, if you like, you know, microvolts. And we need to have a certain amount of decimal points included with the result. Can't really use integers at this point because it would only take us to like 1 millivolt at a time. We need to be a bit better than that. Load in from the read channel function. Now I'll just scroll down to read channel here. This is the function we're calling. This is read channel. We're just basically setting up a local variable called voltage. ADC.isBusy is a question to say basically, is the ADC ready to give us an answer? Was the last conversion successful? Has it finished? So this is telling us if it's busy, and if it is busy, we're just going to wait into a sort of like an infinite loop until it's not busy. So this is just waiting basically. Once the conversion is ready and it's not busy anymore, load in the value using adc.getResult _ MV for millivolts. Now you can read it as volts. There is another version of this which is just _V for volts, but we want millivolts, so we're using this to load in the actual value over the I2C bus from the ADC, and that comes into this variable here, voltage, and we're just returning it. So whenever we call read channel, this little bit of code here is reading the result from the ADC. So let's go back to the code. Little bit of overrange code here. I'm not going to go too much into all of this, but basically if the voltage is over a certain range, and we've got it set at the moment set to a maximum of 250 millivolts, then we'll basically put some information on the screen just to say you're overranged. Now what that means is when the probes are not connected to anything, you know, so it's like high impedance if you like, the constant current generator will be trying to raise its voltage to as high as it can go to try and get that 10 milliamps to flow through the circuit. Of course that's never going to happen because there's no connection, there's no trace, or the probes are not shorted together or anything. We're at high impedance, so what happens is it just goes to its highest voltage. Now its highest voltage will be, I don't know, it's something like probably VDD or +5 volts. It'll try to go as high as it can, probably up to the rail or somewhere near the rail. Never actually measured it yet, but it will be a lot higher than 250 millivolts. So at that point we're going to get an overrange situation, which is correct, just like a multimeter would do. Now if the range is under the overrange limit, in other words it's valid and we're below 250 millivolts in our case, then we can actually start to do stuff. So what I'm doing here is just some simple adjusting the display to keep all of the decimal points in line. Okay, when you have it displayed, all the numbers will have the decimal points at the same position, with everything on the left and everything on the right doing what they want to do, but the decimal points will be in the middle. It's just a neatness for the display. That's all this is doing, nothing to do with any calculations, purely for display purposes. Okay, now we're actually getting somewhere. So eventually we'll get to this code here. Ohms, which is a float value, is voltage divided by 1000, and then the whole thing over the divided by the UUT current. So this is Ohm's law. Basically it's V over I, so R equals V over I. Do you see that? So quite simple really, and what we're having to do is divide the voltage by 1000, because the voltage has been expressed as, if you like, as millivolts. It's not being expressed as volts. So that's all that's doing, taking our voltage reading and dividing it by 1000. Then the whole thing over the current, which is 0.01 of an amp, 10 milliamps in other words. So yeah, that's basically given us an ohm reading, a resistance reading, using V over I. Okay, then a little bit more display stuff. You'll notice we've got something very similar to this display correction here, which is just doing all of the decimal point stuff, keeping everything in line. We've already talked about that. Well, we'll do it again for the ohms, the resistance reading. And we output the resistance reading right there to 3 decimal places. I chose 3 instead of 2. I don't know, maybe I've gone a bit too far. Probably don't need 3 decimal places. But again, this can all be adjusted. Now, at the very end, we've got this little bit of code, which is checking to see if our minimum trip point has been reached. In other words, we now have a valid continuity. It's below our preset point. And our preset point, if you remember, is currently set to 0.5 of an ohm. In other words, if the resistance, ohms, is less than our trip point, I guess you could say equal to or less than and equal to. If you wanted it to actually trip as soon as it hit the point, I've left it as less than to make sure it actually goes below the point. Once that condition's true and we've hit the set point, we can then, again, a little bit of display here on line 2, which is the 3rd line down from the top, 0, 1, 2 from the top. So now we've got line 2, and just print a load of boxes, or in this case I've just got like a load of zeros or a load of capital, I think it's capital O, letter O there, but I'm going to find some better characters. And all this is just an indicator bar. You sometimes see this on test meters where there's like a bar will show across the top of the display or across the bottom of the display, and it's just a sort of a visual indication of, yeah, we've got the we've got continuity. Then we've got buzzer on, which basically turns on our buzzer, which again, as I said before, I haven't exactly decided if we're going to do this internally in firmware or we're going to have some sort of external buzzer system, maybe it's with a key and transistor to turn the buzzer on and off. Different ways to do that. So I'm just calling a little bit of a function down the bottom just to flash an LED off at the moment. And once that's done, for the beep time of, I think we've set it for 300 milliseconds. Once that's done, then print this big space here, which basically clears all of the zeros. So that just basically, you get a line of zeros, you wait 300 milliseconds and you get a bleep, and then you get spaces which clears all of that indicator bar away. And that's it. Then we're in the loop and the whole thing starts again. So in this loop, we're basically reading the value, doing some decimal point shifting, checking for an overrange condition in case the voltage is too high. We're doing a bit of Ohm's law calculation to figure out what the resistance is, and then displaying that again with some decimal point correction. And then we are checking for the all-important minimum trip point. One of the important things we've got to remember when we're designing this is that the duration of the contacts, when you put the probes together, as we're scanning across the PCB tracks, you may want to do it very quickly, like if it's a header that you're checking to with multiple pins, or an edge connector, or the side of a chip, you may just want to run the probe along. This software needs to be able to react quickly. You don't want it where you've got to keep the connection there for 100 milliseconds, 200 milliseconds before the thing reacts and realizes, you've got continuity. We'll want to try and capture that as fast as we can, really. This may take a little bit of experimentation to get exactly what we want, but I've got a feeling it's going to be fairly quick to start off with, and we should be all right for the purposes that we're trying to achieve here. And that's basically that's the firmware so far. Right, now let's move along and get back to the bench and see what we can do with the circuit. Right, so next progress, we have this rather messy lash up here. I've added a couple of features that you can probably see straight away. A couple of things. We have a speaker here, which is being driven from one of the port pins from the Arduino. I've got a little 220 ohm resistor in line to limit the current going to the speaker. It's not very loud, but it's audible and it's good enough for testing. We may want to amplify the signal with a transistor so we can actually drive the speaker a little bit harder if we want it louder. But for now, it's coming straight from the port pin with a 220 ohm resistor limiting the current. You'll notice I've also changed the LCD because the one that I was using, this green one, wasn't very good. I couldn't adjust the contrast correctly, so I managed to get some nice blue ones. I've added an LED in here. There's a yellow LED there. You see that in a moment. So what's the speaker all about? Well, we've added a bleep tone. So now when you go below the set point, you will get a bleep. Just as a little bit of fun, when you first turn on the unit, I've got like a little bit of code in there to play a scale, a musical scale, which probably would annoy some people. But personally, I think it's a little bit of fun. I'll reset the Arduino and have a listen to that. And it plays a little tune. I'll do that again. I've extended the where the 1 ohm resistor was in there. It was too difficult to operate, so I've brought it out to a couple of croc clips here. By the way, at the moment it says over. I hope you can see that. What I can do is I'll zoom in later, but basically that's showing it's overranged because we are, in fact, this is our 2 probes, if we like, with crocodile clips at the moment. So we're open circuit, which is correct. So let's put a 1 ohm resistor across the probes. Don't forget there's a little bit of loss because of the cables and everything, plus the way the protoboard's actually connected. As I mentioned before, the contacts are really quite terrible. So now we're getting a reading of 1.033 ohms, which is pretty much correct. It's a 1 ohm resistor on here. So you can see the screen, and we've got 1 ohm. It's actually 1.03 ohms, and the millivolts across the resistor is now 10 millivolts, 10.33 thereabouts. Okay, now our set threshold is 0.5 of an ohm, so we're not low enough yet. But let's remove the resistor, our 1 ohm resistor, take that off, and let's just try shorting out the probes. There you go. And you notice we're getting an indicator bar as well on the screen. And somewhere in there the yellow LED is lighting up as well, if you can see that just down there somewhere. I know it's a bit difficult to see, sorry about that. I'll try and move the camera angle slightly. Yeah. Now if I keep these shorted together, you'll notice it's a continuous beep with a bit of a gap in the middle. There's a reason for that. Okay. And it's showing us 0.1 of an ohm. It's showing 0.1 of an ohm there on the screen. So this is actually reading as 0.1 when it's shorted together. And so that's basically it. So the 1 ohm resistance, which could be considered as a faulty track, does not operate the bleeper, but you can read the resistance. And when we go below half an ohm, in our case 0.1 according to this, you get the beep. Now how fast does it react? So I'm just going to touch these together quickly. Not that quick. Right, try it again. Yeah, so it's a bit hit-y miss. It's not too bad, but I think it could be a little bit better. Really, that should be reacting immediately. You know, as soon as you touch those together, it should react. So I think we need a faster scanning time for the ADC. And there's a way we can do that. There's a few things we could do here to make this better. I'm just going to check the resistance at that point. Yeah, 0.1. That should easily be. It could just be the resistance of the probes, you know, of the croc clips. Yeah. If there's any dirt on the contacts or anything, it won't. Yeah. So I think we might have to speed things up a little bit in the scanning loop, but basically it's kind of working. You could probably use that as it is. We've got an audible bleep now, so we can get through a test board fairly quickly. We've got a set point of 0.5, which, okay, at the moment that's hardwired into the firmware. If we had a couple of buttons, we could adjust the set point externally, which is something we should really do. and also have a button or a method, maybe press both buttons at the same time or something, and then that would allow the nulling of the probe. So you short the probes together, press the two buttons together or something like that, and that would null out the resistance of the cables, and then you'd get like 0.0 ohms ideally. So there's a couple of enhancements we could do here, and probably have a look at the firmware and see what we can do. But that's where we are so far. Not bad. Okay, so here we are back in the Arduino IDE, and let's have a look at some of these enhancements that we just made. All of this is the same at the top here, no change here. You'll notice we've got some defined musical notes, and from C6 on a scale up to C7, and also we included C8, which is an octave above C7. Now, what's all this about? So this is so we can play musical notes if we want to, and we also have this note here, C8, which is an octave above C7, and this is our actual beeper when we put the probes together and we get continuity. That is the actual, if you like, musical note that we play. These figures here are not in hertz. If you go look up a lookup table on the internet and you look what frequency in hertz, like say C6 is, it's not 955 hertz. So we've done some pre-calculations here to basically allow the Arduino to not have to calculate this later. If you like, we're saving a bit of time by doing the calculations already and hardwire them in here. So it's calculated by this. It's basically 1 over the frequency, that would be in hertz, times 1,000,000. And by doing that little bit of maths there, you end up with a figure which is suitable for putting in delays for, you know, actually playing the note in a loop. So if you have a delay for, let's say, turning the port bit on, and then you have another delay after that for turning the port bit off, you produce a square wave at that frequency. And basically, if you follow this little bit of maths here, you can figure out what these values have to be, and that's what you send to the, if you like, the function which plays the musical note, and that kind of works out correct. I'll show you the little musical bit at the end. We've got a little bit of code here called play scale, and that's what we call when we first turn on the unit. You'll notice we've got C6, D6, E6 all the way through to C7. That's our 8 notes that we play, and we send that to, we call this function buzz, for a duration of 75 milliseconds per note. So it's quite quick. You don't want it to take too long, and some people would probably even just disable the whole thing. They don't want it to. I know some people don't like musical things when you turn things on, and personally I don't have a problem with it. I think it's quite fun. So at the bottom we have this function called buzz, and this is the part of code which plays the note. So you have a musical note, a parameter there, and you have a duration parameter there in milliseconds. So, and again, these notes are the ones that were pre-calculated as our scales, if you like. We're doing a little bit of compensation here by taking the duration that we want and a little bit of maths. What this does is it figures out what the durations need to be, or, you know, in order to play the note at the correct length. So depending on the frequency, so that actually depends on the frequency of the note, okay? And we do a little bit of compensation in our for loop here, which is down here, which basically plays all of this and actually produces the square wave. This digital write turns the pin on, then you delay for note delay time that we've calculated from the table, from the defines. Then you turn the pin off, and then you have another delay, and this produces a square wave, and that's exactly what's going on through the port pin, which drives the speaker. Pretty simple. It's not too complicated. We also have the LED which turns on as part of the continuity test, and we also, when we're finished, we'll turn off the LED as well. So that's just turning the LED on and off those bits. You'll notice we'll have this function here which is no interrupts. It's debatable whether we actually really need this or not. I tried removing this and it didn't make any difference. But good practice, if you want a clean tone, like say a musical note, and you don't want any interference or changes in pitch or anything, it's a good idea to turn off the interrupts within the Arduino, so it's not going to be pulled away while it's trying to produce a square wave and go and do something else in the middle of it. Could cause a glitch, could cause a change in the pitch of the actual note. So good practice is just basically turn off the interrupts while you're doing it, and then when you've finished producing your beep, if you like, put the interrupts back on so it does everything else as well later on. Now, like I say, I've tried taking these out and I couldn't really hear any difference, but I've left them in anyway. So there you go. So these two functions here, play scale and this one buzz, is all we need to do to produce our musical notes and our beeper. What else have we done? Let's have a look at the code. We've got a beep time. This is the duration of the beeper, 300 milliseconds. Seems to be about right. Had a bit play with that and just experiment with different values. Kind of feels quite similar to my fluke test meter that I use. You'll notice we've got a delay in here of 10 milliseconds. Now, if you remember, I'll just quickly see if there's any other changes that we've made. No, not really. Everything else is the same. Right, so if you remember, when we were looking at the display earlier on, it was kind of flicking on and off. The right-hand side digits were not very clear. It's as if it's been written too quickly. Now, this is an interesting problem to have. We want to be able to scan the ADC, pull the ADC as fast as possible, as fast as it will allow us to do so, so it can react to the resistance going below the set point as fast as possible. But on the other hand, we don't want to be trying to update the display in the same loop at that speed, because as we can see, it does cause a bit of disturbance to the digits. Now, what we can do, and that's what I'll probably do right now, we can alter the main loop, this whole thing, our main loop here. Rather than trying to do everything in one loop, we can have a sectioned off loop, like if you like a loop within a loop, where the ADC loop can be running at maximum speed, but the display updates could be, say, doing 1 in every 100 or 1 in every 50, something like that, a little bit of experimentation to slow down the update rate of the LCD display. That stops the display from flicking all of the time, gives us a nice clear reading that we can see, hopefully right to the right hand side digit as well. But the ADC is running on the outer side of that loop, and that will be running at maximum speed. So we're going to change this, and we'll change it so we are basically updating the display slower than what we are reading the ADC. The minimum trip will have to be in the fast loop, if you like. This needs to react as soon as we can. Probably remove this delay completely, and at that point we can basically try and get the loop to go as fast as possible. Alright, so here we are back again with the updated firmware, and I've got my yellow cursor back. I do apologise, I didn't switch it on the last segment. Hope this is clearer. This is our main loop now. Now you'll notice that it's actually a lot shorter than it was. We've made it a little bit more structured. What I've done is removed all of the actual display side of things and put it into this function here, do display. So this is the same code as what we had purely for displaying to the LCD and doing our decimal point shifting and that kind of thing. Display of ohms at the bottom as well. Over range checking is in here. So yeah, this is all of the writing to the LCD display now in a function called do display. We are passing in a float voltage and a float ohms parameter. So those, or this function rather, is now being called from the main loop. That's why it looks shorter. So I've basically shifted it all out to a separate function, and there's a reason why I've done that. So let's have a look. Now what we've got here is now two loops, if you like. We've got the main loop, which is all of this here. So all of this has been continuously executed. Every time it gets to the bottom of the function, it starts again. We all know that. That's the, if you like, that's the outer loop. Now But now we have this bit of code here, which is the inner loop, and what this is doing is everything to do with reading of ADCs and testing for the set point, which is what I've set there in the comment basically. Set up a, if you like, a counter called disp loop, which is just an integer, and if it's less than 200, then keep going. So all this code here will be continuously looping as fast as it can. There's no delays or waits in here. It'll go as fast as it can 200 times. When it gets to 200, you notice there's an increment at the bottom there, which steps it up every time it loops. It increments by 1. When it gets to 200, then it stops, and then it will execute whatever's in the outer loop, which is our display function. So I hope you can see that everything in this while loop is going to be going 200 times faster than everything that's been done on the outer loop, and all we have in the outer loop is our display function, which writes the values to the LCD display. That's exactly what we wanted. We wanted to be able to read the ADC as fast as possible and react to the set point value. And there's our reaction to the set point value just there, our checkpoint there. And if ohms is less than the trip point, then do all of this. So this means that we now have a much faster reaction time to the probes being shorted together. When we do an actual measurement test, the reaction of the unit will be better, and we'll see that in a moment. We'll see exactly how much better it is when we get it back on the bench. Now you'll notice this is the reason why I took out the display code and put it in a function called do display. Now why bother? Why not just have all of the display code in here? Well, it's because we'll want to call it again when we get a trip, when the actual set point is reached. If you didn't have the display in here, it means you wouldn't see the value of the of what was on the screen for the what actually made it trip. So when you hold the probes together, or you have something below 0.5 of an ohm, then it would, we want to be able to see what that value is. Is it 0.1 of an ohm? Is it 0.2 of an ohm? Is it pretty close, like 0.49 of an ohm? You want to be able to see that, and if we didn't have it in here, you wouldn't see those values. It would simply give us a beep, and you would know, okay, we've reached the set point, but we wouldn't know what the value was, and it could be of interest for whatever reason. So I've included the display function also in the test for the minimum set point. So now when you put the probes together, we should see the actual value being displayed, whatever it is that's making it trip. So that's why we took the display code out of the main loop and put it into its own function, because basically we need to be able to call it in 2 different locations. That keeps the display up to date at a reasonable rate. It's not being updated at maximum speed, which usually causes a problem to the LCD digits that can get a little bit difficult to read, get a bit mushed up. It doesn't really respond. The refresh rate of the LCD display, in case you're not aware already, it's pretty slow. You can't really make updates to LCD very quickly. It takes a while to react, so the refresh rate is usually quite poor. It's best not to try and write to it too quickly, otherwise you just end up not seeing digits. You could adjust this value of 200. If you wanted to slow the display refresh time down, you could make it 300, you could make it 400 if you really wanted to slow things down a bit. I've just had a little bit experimentation, and 200 seems to be fairly reasonable for the speed of what everything's actually running at. We're running the Atmel on a 16 megahertz crystal clock, by the way. So I hope you get a feel for what's actually going on here. It's a loop within a loop. This will run as fast as it can. There's no delays in here. Once it reaches 200, it branches out, and then it does the display update. And then once the display is done, we go right back to the beginning and do the whole thing again. So let's get back to the bench. Let's see if those probes are reacting any faster. Okay, so here we are with the updated firmware, with the changes that we just made. Well, okay, everything looks the same so far. Let's try getting our test probes here, and first of all we'll measure the 1 ohm resistor that we have. I hope you can see that's measuring 1.027, 1.028 of an ohm, and What's important is we can now see the right hand digits quite clearly, right at the end of the display. It's not flicking around too much, it's not trying to write to the LCD too quickly. That's a reasonable speed that we've got there, and that's because of the 200 loops that we're waiting for while the ADC's been read before we actually write to the display. So that's a much better display. It seems to be a lot more stable and easier to read. So we've cured that problem. What about the actual detection speed? So all I've got here is my 2 probes, and let's just see if I can short the probes out. We'll just make sure we can hear that first of all. Yeah. Now how fast can we go here? I'm just going to flick these together. Very good. I'll try and keep this in focus. I do apologise. I hope you can see that's immediate. I'm literally just touching it very, very quickly indeed. Oh, I actually missed that one. That was my fault. There you go. I missed that again. That's me just like not aiming correctly. There. And it hasn't missed a single one. So that is absolutely perfect. Great stuff. So then I'll go back to the 1 ohm resistor that we have, our test 1 ohm resistor, and there we are, 1.03, and the milliamps range is 10.3 milliamps. We're at a point where this is a workable project. We've got the reaction time of the probe good, we've got the set point to actually react fast, the display looks clean, you know, we've got sound, we've got a bleeper, and we've got a little LED for whatever purposes that we decide we want to do. Really the only thing that would be left with the project would be, with the design of this project, would be to add a couple of buttons. That's probably going to be next. So then we could set that set point to anything we like, and maybe do a few other things as well. Importantly, we need to be able to null out the probes, so when you actually short this out like that, then you short the probes out, do the null, whether it's 2 buttons or 1 button or whatever, and then it would cause an offset to be created, a relative reading, and then we should get all zeros. So there's a couple of things we need to do: buttons for the set point, and a way to nullify, to actually you know, do a relative reading. But other than that, I think we're good. We're probably at a point of the video, it's already a bit long. We've got the firmware nailed down well enough for now, possibly some improvements with buttons. We've checked everything and it's actually working. So I think this is going to end up being a 2-part video. We've got the design more or less nailed down. We just need to, you know, get the circuit into keycard. To be honest, there's not that much, but we do need to maybe design a PCB, mount the display onto the PCB, possibly use a surface mount Atmel 328P, put that on the board as well, and you know, the other components, and the ADC module of course. Put all that in a box. I think then it's like job done. A couple of buttons on the front maybe. So that's where we're at the moment. I hope you have got something from this whole design thought process that I've been going through, and making changes as we go. That's it's quite important that you review where you're up to before you try and, you know, progress to the next stage. You know, so I hope that's been of interest to you if you're new to electronics or new to you know, developing your own designs. I really wanted to show the process involved, and it's relevant to anybody that wants to design electronic equipment, I think. So we're going to stop there, and probably in part 2, might take a little bit of time. I've got to, you know, probably design a board and this kind of thing. But hopefully in part 2 we'll be looking at putting this onto a board, keycard circuit diagram rather, then onto a board, and, you know, actually finishing the thing off. And hopefully at the very end we'll have it in some sort of a box, and we'll end up with a piece of test equipment that would be of real use on the bench. I'm quite happy with the way this is working right now, and the reaction time was a bit of a concern for me, but now it's pretty much immediate. So that's good enough. If you've got a PCB like something like this with a connector on the end of it like that, and you want to test the traces, you may want to take your probe, you know, and just kind of like just run them along like that, and it's got to be able to pick up that sort of speed of each pin, and as you've seen, it's doing exactly that. It's completely quick, so that's totally usable. So I'm going to end the video there, come up with a part 2 later, and we'll get this onto a PCB and we'll, you know, finish the project. I hope this has been of use to you. Do comment if you want any extra features added, if you think maybe something could be better, maybe as we're doing it, and you know, you might be able to think of a nice handy feature that could go into this, or before we start putting it onto a board. But feel free to comment, and thanks very much for watching.